Okay, let's start the class. Good afternoon. How are you? Medyo numinipis tayo, ano? Okay, we're in the final stretch of EEE 131. We only have two modules left, Module 5 and Module 6, each one taking 2 weeks. So we're in the last 4 weeks. No? Tapos na tayo sa 60% of the course. Andun na tayo sa last 40% of the course. No? Now, this is the part of the course which probably you are going to be most challenged by. I'm already sort of giving you a heads up. No? Medyo these last two modules are going to be quite challenging, especially the last. No? So please try to keep up with the subject matter. After my suggestion, after every lecture, you review the lecture and try to assimilate the knowledge. Okay? Because if you make yourself, if you delay studying the material, then medyo mahihirapan kayo. No? So that's just my suggestion. Okay, so what are we going to take up today? Or in this particular module, we're going to take up small signal analysis of transistor amplifiers. In the last two modules, Module 3 and Module 4, we took up the small signal model of the transistor itself. No? But this time, we're going to take up the analysis, the small signal analysis of the entire amplifier, meaning to say the transistor and all its corresponding external components. So this is what is going to be covered in Module 5. First, I'm going to reintroduce two-port networks. For those of you that attended my online sessions, I did a short introduction to two-port networks when we first took up the small signal model of the transistor. I'm going to reintroduce that. And then we're going to go to common emitter, common source amplifiers. Then common emitter, common source amplifiers with the generation resistor. The generation resistor, pag linagyan natin ng resistor sa emitter, kaya linagyan natin ng resistor sa source, you call that a degeneration resistor. And the reason why you do that is because it generates the gain. So we're going to take that up. And then we're going to take up the small signal analysis of other transistor amplifier topologies. So take note that we are no longer going to separately treat the MOSFET and the BJT. They are now going to be treated at the same time. Because there are similarities between the MOSFET topologies and the BJT topologies. So we're going to take that up at the same time. Okay, let's start with two-port networks. And I said I already sort of gave a primer on this when we discussed the small signal model of the transistor. When we have a linear circuit, so this is a linear circuit, with respect to two particular ports, so in this case, we can think of this port as your input port, and we can think of this port as your output port. With respect to two particular ports, you can represent the entire circuit using a two-port network model where you only need to specify 4 parameters. Okay? So this particular circuit can be a really complicated circuit that can consist of tens or even hundreds of components. And you can reduce that to a model where you only have to specify 4 parameters. So that's the essence of a two-port network. Now the caveat is this: your linear circuit must not contain any independent sources. Pag sinabi natin linear circuit, ang ibig sabihin nun, your elements are linear elements. So what are your linear elements? You have your resistors, your inductors, your capacitors, okay? And then your linear supply voltages. And then you have dependent and independent sources. But in using two-port networks, we must make sure that the network does not contain any independent sources. It can contain dependent sources. So pwedeng magkaroon ng voltage-controlled voltage source, voltage-controlled current source, and so forth. Ano? Pero hindi pwedeng magkaroon ng independent sources. So there are 4 variables associated with a two-port network. So at the input, you have V1 and I1, the voltage and the current. And at the output, you have V2 and I2. By the way, how do you know that a port is indeed a port? Paano natin malalaman na talagang port ito, no? The rule is this. If the current entering one terminal is equal to the current leaving the other terminal, then that is a port. So if I draw this, no, this should also be equal to I1. Okay. By the way, this is not necessarily an open circuit, no. In other words, there can be something connected here, and there can be something connected here. Kasi kung wala naman nakakabit sa input, syempre yung current natin zero, no? Kung wala nakakabit sa output, yung current din natin dun is zero. So this is not necessarily an open circuit or this, okay? And then like I said, the current entering one terminal should be equal to the current leaving the other terminal. So dito naman kung I2 yan, dapat ito I2 din. That is how you know that it is a port. So there are four variables associated. So at the input, you have V1 and I1. At the output, you have V2 and I2. Then I already mentioned this, four parameters needed to completely describe the network with respect to the two ports. And the parameters will depend on what are considered to be the independent and dependent variables. So let me give an example. If my independent variables are I1 and I2, and then my dependent variables are, V1 and V2. Okay. Are you familiar with matrix notation? Are you okay with matrix notation? Okay. Okay. So you express now your dependent variables in terms of your independent variables. No? So if I use matrix notation, this is V1, this is V2. Okay. This is I1, this is I2. Okay. And your matrix will consist of, okay, let me just Z11, Z12, Z21, and Z22. So in normal notation, ano ibig sabihin nito? This is V1, this is Z11 I1 plus Z12 I2. And V2 is Z21 I1 plus Z22 I2. Anyway, the point is this is your dependent and this is your independent. And this is what you call now your impedance matrix. It is called your impedance matrix because the units of your matrix elements are in ohms. No? These are in ohms. Okay. So your impedance elements convert current to voltage. Okay. Convert current to voltage. No? You have a current I1. You want to convert that to a voltage, you multiply it by Z11 I1. And that will be a component of V1. Current I2, you want to convert it to a voltage, you multiply it by Z12, and that will be the second component of V1. If you take a look at these two equations, they actually look like KVL expressions. Pag tinignan nito, this look like KVL expressions. And I can draw a circuit model. What is my circuit model going to be? Okay, let's start at the port 1. So you have V1, you have V1 here. What is V1? V1 consists of two elements. First is Z11 I1. Now your I1 is supposed to be entering port 1. Okay, what will represent the voltage Z11I1? That will be an element that is an impedance. No? At this point, let's just assume it's a resistance. So this is going to be Z11. Okay, then you have a voltage term that is external to this particular circuit, because this voltage term depends on I2, and therefore that must be a controlled source. It must be a current controlled voltage source. So what I'm going to have here now is a voltage source where this is now J12 I2. So that makes up my input side. And then my output side is going to be very similar. No? This is going to be Z21 I1. Okay. And then this is going to be Z22. Then I have V2. And then the current entering this is I2. And usually you have a common, you have a common ground or a common reference for your voltages. So these are connected. This is to make the reference for V1 and the same. So this is now your two-port model. Okay. Where you have 4 elements inside the model. Okay. Again, you call this your impedance parameter. So it depends on what your independent variables are and what your dependent variables are. Okay, in electronics, we usually use what we call the hybrid parameters. Okay, bakit natin tinawag na hybrid? Dahil yung units ng element ng transfer matrix ko are not consistent. Nag-iiba-iba. That's why we call it hybrid. No? Dito yung units nito, yung units ng elements dito, are all in ohms. Dito, ang units nito ay iba-iba. No? That is why you call it your hybrid parameters. Okay, so you have V1. V1 is equal to H11 I1 plus H12 V2. Remember, these are your dependent and these are your independent. And standard yan, no? Sa hybrid model, the independent are the input current and the output voltage. That's standard in the hybrid model. No? Kung ano man yung input current at saka yung output voltage, yun yung independent. And then the dependent, of course, would be the other 2 variables. That's your input voltage and your output current. No? Okay, so V1 is H11 I1 plus H12 V2, and I2 is H21 I1 plus H22 V2. Okay. Now, if you take a look at these 2 equations, what does the first equation look like? What does the first equation look like? Dun sa dalawang circuit laws, what does that look like? Application of what law? Anyone? There are only 2 fundamental circuit laws, di ba? Natutunan nyo sa 1, 2, 3. What are they? Kirchhoff's voltage law and Kirchhoff's current law. So if you take a look at the first equation, this looks like the application of KVL. No? And if you take a look at the second equation, that looks like the application of KCL. Right? So this looks like a mesh equation, and this looks like a nodal equation. Do you see that? No? Kasi ito voltage, ito current. No? So we can draw the corresponding model for this. Okay, punta muna tayo dun sa V1, no? V1 is at the input. Okay, so I have plus minus V1. And what enters this is first I1. Okay, so I have here a voltage term, H11 I1. So what is H11? What is H11 going to be? What type of element? Lakas-lakasan yun. Nahihiya kayo. It's okay to make a mistake. What is it going to be? Resistance, right? H11 is going to be a resistance. It converts a current to a voltage. Okay, so this is going to be H11. Okay, your second term is external to this particular loop or mesh. The second term is external to a particular loop or mesh. Therefore, it must be a controlled source. What type of controlled source is it? Is it a controlled current source or a controlled voltage source? What specific type? It's a voltage controlled voltage source. Okay. So here I have a voltage controlled voltage source. So we use the standard symbol, which is a triangle, voltage controlled voltage source, where the value is H12 multiplied by V2. Okay. So yun yung una equation natin. We're talking about the H parameter model. These are your H parameter models. Okay, then I2, this is a nodal equation. Right? So what do I have? I have here, dito sa, okay, I have here, this is going to be V2 plus minus I2. I2 is going to split into two components, right? I2 is split into two components of H21I1 and H22 V2. Okay? Dito muna tayo sa H22 V2. H22 converts a voltage to a current. H22 converts a voltage to a current. So what is H22? What type of element is H22 if it converts a voltage to a current? Conductance. Okay, conductance. So how do I draw my conductance? Well, I can draw it as a resistor. And the value of the resistor is 1 over H22. Okay. This is a conductance. To convert that to a resistance, I have to get the reciprocal. No? So that's one component of the current. So we're doing a nodal analysis on this node. Dito sa node na to. So you have another component. This is H21I1. No, yung I1 wala dito sa node na to. It's external. So this must be a current controlled current source. Okay. So this must be a current controlled current source. Okay. Yung direction ng current, ito pababa dito, ito pababa din dito. So this will be in this direction. Okay. And this is now H21 I1. Okay, and then again, because you have the same reference for your voltages, typically you have the same references for your voltage, then you connect these two. So this is called your hybrid model. Yeah. Okay, you have terms for your different parameters. Okay. Yung H11, okay, how do I determine H11, no? How do I determine H11? Okay, if I short V2, that is, if I make V2 equal to 0, then this becomes 0. Right? So H11, if port 2 is shorted, V2 becomes equal to 0. No? And therefore V1, which is equal to H11I1 plus H12 V2, ito 0. This will be 0. So what is H11? H11 is equal to V1 over I1, okay, with port 2 open. With port 2 open. We say V1 over I1 evaluated with port 2 open. Sorry, port 2 shorted. Ano ba naman? Port 2 shorted, no? Sorry. Port 2 shorted. And you call this your short circuit. This is your short circuit input resistance, no? Or input impedance. Short circuit input. In general, you say impedance, no? Short circuit input impedance or short circuit input resistance. Okay. What about H12? Okay, H12. If I leave yeah. If I leave V1 open, okay, then that means I1 is equal to 0, no? If port 1 left open circuited, then ibig sabihin I1 will be equal to 0, no? So even kung bukas, hindi ako magkakabit ng kahit ano rito, kung wala akong ikakabit dyan, itong current na to will be equal to 0. Okay? So what will be the value of H12, no? If we take a look again at this equation, we have V1 is equal to H11I1 plus H12 V2. So this is going to be 0. Or H12 is equal to V2 over, V1 over V2. This is V1 over V2, no? This is port 1 open. And you call this your open circuit reverse voltage gain. Reverse voltage gain because it's the gain of your input over the output, no? Kasi usually ang gain, pag sinabi natin gain, it's output over input. Pero in this case, it's over the output. Okay. H21. Okay. How do I get H21? Ito naman, no? H21. Okay, if I leave V2 open, okay, if I leave V2 open, then I2 is going to be equal to 0, no? Oh, sorry. Short circuit. No, that's not the way, no? If I short V2, then I2 is just going to be H21 I1. Okay. If again, no, if port 2 is shorted, that is V2 is equal to 0. Okay, ano yung equation natin? I2 is equal to H21 I1 plus H22 V2, no? I2 is equal to H21 I1 plus H22 V2, no? So this is going to be equal to 0. Or I2 is just going to be H21 times I1, no? Kita naman yan, ano? If you short this, then all of the current here will flow through your short. None of it will flow through this. Therefore, yung I2 natin will be equal to this particular current, no? And so what is now H21? This is now going to be I2 over I1. No? So this is port 2 shorted. Okay, and you probably can guess what the name is going to be. No? This is your short circuit forward current gain. Short circuit forward current gain. No? Let's just shortcut the H22. No? H2 is going to be called your open circuit. No. So I'll just write it here. No? H22 is going to be equal to I2 over V2. No? I2 over V2 with port 1 open. Okay. I2 over V2 with port 1 open. No? And this is going to be your open circuit output conductance. Okay. So those are your H parameters, hybrid parameters. And usually ginagamit natin to sa electronics. So E131, we're going to tweak this a bit. Iti-tweak natin to. No? Itong model na to, we're going to tweak it a bit. And the tweaked version, we call the bilateral hybrid pi two-port model, or bilateral hybrid pi two-port network. So this we're going to use in E131 for small signal analysis of transistor circuits. So it's the same principle. This is your two-port network. Let me shift to input and output, no? I and O. Kasi yung ginagamit na sa mga libro, no? So this time, hindi masyadong malinaw what your independent and your dependent variables are. In fact, you cannot peg it, no? Kasi dito sa first expression natin, you have VI as a function of I input current and output voltage. So it appears here that this is your dependent, no? Pero pag tinignan naman natin dito sa expression sa VO, lumalabas yung VI, no? So hindi talaga malinaw, okay, what are your independent and your dependent variables? That's the nature of the bilateral hybrid pi two-port model, no? The important thing is you express VI in terms of your input current and output voltage, and you express VO in terms of your output current and input voltage. So there are two particular equivalents. The first we call the Thevenin equivalent. The Thevenin equivalent of this. No? Okay, how do you get the Thevenin equivalent? Okay, let's go back to this. Okay, ito mukhang Thevenin equivalent na ito nasa kaliwa, ano? Ito nasa kaliwa, mukhang Thevenin equivalent na yan, no? Okay, ito, this does not look like a Thevenin equivalent, no? How do you convert this to a Thevenin equivalent? Okay, do you remember? Yung voltage to current or current to voltage interconversion dun sa EE123. If you have a current source with a voltage that is with the resistor that is in parallel with it, you can convert that, ano? Kung meron akong current source, you remember this? okay, or the current source, and I have a resistor in parallel, no, I can convert this to a voltage source with a resistor in series. Okay. Anong value nitong voltage source na to? You remember? You don't? IR, that's right, no? Okay, the answer say it, no? So this is IR. And what's the value of this resistance? That's going to be equal to R. No? Okay, my point is we can convert this. We can convert this to its equivalent voltage source. And when we do that, we come up with the Thevenin equivalent of your bilateral hybrid tie two-port model. I'm going to change the terms for the parameters. Instead of H11, we'll call it Ri. Okay. Instead of H22, we'll call it Ro. Okay. And then instead of, you remember, okay, dito, instead of H12, okay, I'm going to call it AR. And then, kung ano man yung equivalent voltage source dito from the previous, okay, that's going to be a function of VI. No? Kasi dito, no? This is a function of, dito it's a function of I1. When you multiply this, no, that's going to be a function of VI. And then I'm going to call this AF. So papalitan ko lang yung mga terms. No? So instead of this having been a function of I1, I'm going to convert it to be a function of VI. And then I change the terms. So this is the Thevenin equivalent. Where your Ri is your input resistance. Okay, your Ro is your output resistance. Okay. AR, you call this your reverse voltage gain. And AF is your forward voltage gain. Okay, kung may Thevenin equivalent, meron ding Norton equivalent. So ang gagawin naman natin dito sa Norton equivalent, again, going back to this, ito naman yung i-convert natin to a current source. This is what we convert to a current source. And so that will come out looking like this. So, pareho yung definition ng Ri at saka Ro. That's going to be the same. Okay. GF, you call this your forward transconductance. Okay. And then GR is your reverse transconductance. Now, these are bilateral models. Ano yung sinabi natin na ibig sabihin ng bilateral? Do you remember? When do we say it's bilateral? Anyone? When do we say it's bilateral? Okay. Ang bilateral, ibig sabihin nun, if you will recall, the input affects the output, and the output can also affect the input. Pag tinignan natin itong left, ano, our output condition, that's VO and IO, has an effect on the input. Because this voltage controlled voltage source, okay, this voltage controlled voltage source is a function of your output. So your output affects your input. On the other hand, your input affects your output, no? Because this voltage controlled voltage source depends on your input, no? So we call it bilateral. Okay, we are going to adopt a unilateral hybrid pi two-port model. That's what we're going to use in EEE 131. This will make your life easier. No, mapapadali yung buhay nyo dahil dyan, no? It has its limitations. So sometimes it will not come up with very accurate results. The results will usually be good enough. Later on in your future courses, when you take up feedback systems, you're going to learn to compensate for these limitations. So how do we convert the bilateral to unilateral? Sa unilateral, habol natin, we're just looking for the input on the output. No? How does the input affect the output? So we're not looking at the other direction. So, madali ano? If we are not looking for if we're only considering the effect of the input on the output, all I have to do is zero this. How do you zero a voltage source? You short it. No? If I'm using the Norton model, how do I zero a current source? You open it. So if I take a look at my unilateral models, ito yung magiging itsura. So dito, yung voltage source ko, I just shorted it. Dito, yung current source ko, tinanggal ko. I opened it or I removed it. So these are now my unilateral hybrid pi two-port network model. So this is the Thevenin equivalent. Pero ang itsurang Thevenin na lang is yung output. No? This is the Norton equivalent. Ang itsurang Norton is just your output. Now notice a change in notation. So dito, ang ginamit ko is AR at saka AF. Ngayon, I just say AV, where AV is my voltage gain. AV is my voltage gain. This is the Norton equivalent. So here I used GR and GF. Dito ang gagamitin ko is GM, where GM is my, what do you call this? G? Anong tawag sa G? Transconductance. Why is it a transconductance? Because the units is, well, the units is the units of conductance, which is Siemens. Yung unit ng G. No? That's the unit of conductance, which is Siemens. But it's not a conductance in the sense that the current across it will determine the voltage through it. No? The voltage across it will determine the current through it, because it's the voltage in another part of the circuit that determines the current through it. Dahil yung voltage is in another part, then it's called a transconductance instead of being a direct conductance. Kaya tinawag ito na transconductance. Okay. Again, no? So this is derived from the bilateral hybrid pi model, the unilateral. Ang ginagawa lang natin, tinatanggal lang natin yung effect ng output sa input. Does this look familiar? Familiar ba yan? Saan nyo nakita yan? Saan? MOSFET lang ba? Yeah. This looks like the small signal model of your transistor itself. No? Actually, MOSFET, wala nito, no? Wala nitong RI. Kasi sa MOSFET, this is yung input resistance sa MOSFET is infinity, no? So this looks like the small signal model of your BJT, or the small signal model of your MOSFET if you consider that R of I is equal to infinity. What is the difference? Okay. The difference is summation. No? Take note that here, all the parameters are expressed in uppercase. Uppercase letters. Yung RI, yung RO, AV, GM, they're all expressed in uppercase letters. When we took up the small signal model of the transistor, we made it a point to use lowercase letters. Maybe I need another slide, no? Okay. So, yung ano, no? Yung model natin, okay, you have RI, GM, VI, okay. This is RO. This is VI, I's of I. Then this is VO, I's of O. No? Okay, if you recall yung BJT small signal model, anong tawag sa resistor na to? Powers of, ano yung subscript? Pi. Powers of pi. Okay. And then this is small GM. Okay. What do you have here? This is VBE. VBE. Okay, then we have small r's of O. Okay. And this is VCE. So you can see the parallelism. Except that, okay, this is when you're talking about entire circuits. Okay. Ito ginagamit when you're talking about entire amplifier circuits. Okay, this is just the model of the BJT transistor. Okay, that's why it's important na sundan mo yung notation for uppercase at saka lowercase, no? Kasi if, for example, if it's your assignment or your exam, tapos ang intention niyo is capital G's of M, pero may kayo ng small G's of M, syempre yung nag-check, sabihin, hindi naman yun yung transconductance ng transistor, no? That's the transconductance of the entire circuit. So you have to be a little bit disciplined in the use of your uppercase and lowercase letters. Okay, understand? Okay. Okay, let's talk about some special conditions. The first special condition is what we call the no load condition. The no load condition occurs when the network does not deliver any output power. When the circuit does not deliver any output power. Okay. So this is your Thevenin equivalent of no load. No? How do you describe no load using the Thevenin equivalent? So we're talking now about the unilateral model. No? So like I said, no, we're going to make your life simple by using the unilateral model. Papadaliin namin yung buhay ninyo. No? So we're talking about the unilateral model. What is the no load condition if this is the Thevenin equivalent? The no load condition would correspond to when I is equal to 0, which means we leave the output port open. If we're talking about the Norton equivalent, that corresponds to no load. No? Okay, if you consider the Norton equivalent, if I leave this open, there will still be a power associated with my output, right? No? Pag iniwan ko itong bukas, dito sa Norton equivalent, there's still a power associated with my output because there's a current flowing through R's of O, and therefore if current flows through R's of O, there will be power dissipated across R's of O. So how do I make that power equal to 0? I short the output. If I short the output, V sub O is equal to 0, right? All this current is flowing through my short, but because the voltage is equal to 0, there is no power being dissipated because power is voltage times current. So if your voltage is 0, syempre your power will be 0. Okay, so again, no, depending on what equivalent circuit you're using, in an equivalent, leave the output open. Kung Norton equivalent, short the output. Okay, so now, how do we determine the hybrid pi parameters? So that's the next thing that we have to do. No? So given this particular circuit, so again, this can be a complicated circuit that can have a transistor inside. It can even have many transistors inside. Ang sinasabi natin, we can reduce this to just 3 parameters. Ngayon, 3 parameters na lang, no? Hindi na 4. Dahil ginagamit natin ngayon is yung unilateral model. So we can reduce this to just 3 parameters. The first is transconductance. So how do we determine the transconductance? Okay. This is our, let's assume it is the this is the Norton model, no? The Norton equivalent. Okay. How do we get the transconductance? Yeah. If I, yeah. Sandali, ano? Yeah, if I short this, no? If I short this, okay, then my I of O is just going to be GM V of I. Okay. So if I short this, no, my I of O is going to be GM V of I. I of O will be equal to GM multiplied by V of I. No? Gaya ng sinabi ko kanina, kung i-short ko to, okay, then all of this current, all of the current here will just flow through my short. Dahil short to, no? None of the current will flow through the output resistance. No? So ang current ko dito lang mag-flow. So I of I will be GM V of I. What is V of I? No? Well, V of I is a test voltage connected to the input. Kasi kung wala akong ikakabit sa input, walang excitation. I will not have any currents flowing. I will not have any voltages or currents. No? Remember in EEE 123, when you are getting the Thevenin equivalent of a circuit with only dependent sources, what do you have to do? You have to apply a test voltage. I don't know if you remember that, no? But you study that in EEE 123. Pag meron kang dependent lang yung sources, the only way you can get the Thevenin resistance is by applying a test voltage. So that's the same case here. The only way I will be able to compute for anything is I have to apply a test voltage here. Okay, from here, what is GM? GM is equal to I sub O over V sub I, no? My test voltage. This is at zero load. No? So zero load is no load, no? No load condition. Maybe I should use the same term, no? This is at no load. That is the value of G sub M. Okay. So I have to apply this test voltage and I have to short the output. Okay. What about voltage gain? No? So ito ang kina-compute ko is yung G sub M. Para ma-compute ko yung voltage gain, what I have to use is the Thevenin equivalent of your circuit. So how do I get now? Okay, how do I get voltage gain? No? If I leave this open, okay, if I leave this open, there is no voltage drop across R sub O. Right? So if output is left open, there is no voltage drop across R sub O. No? Therefore, V sub O will just be equal to AV V sub I. Therefore, this voltage will just be equal to this voltage, the voltage drop across R sub O. No? Again, where V sub I is a test voltage applied at the input. Okay. So ito yung test voltage natin, I leave this open. So how do I compute for AV? AV is simply V sub O over V sub I, okay, at zero load. What is zero load pag Thevenin? Zero load pag Thevenin, you leave this open. Okay. So we now know how to determine A sub B. What about output resistance? Okay. So how do I get my output resistance? What I want to do is, okay, I want to reduce this to 0. No? I want to reduce this to 0. So to reduce this to 0, what I want to do is, I want to make it 0 input. 0 input para ito maging 0. No? Okay? 0 input, I leave this open. Okay? Well, actually, 0 input, depending on whether it's a voltage source or a current source, you either leave it open or you leave this closed. No? But in this particular case, it doesn't matter. Because if I leave this open, okay, then I sub I is equal to 0, and V sub I will be equal to 0. If I short this, then V sub I is also equal to 0. No? So what is my output resistance at under these conditions. No, this is zero input. So this becomes zero. Okay, and R sub O is just VI over a V. Sorry, this should be VO, no? R sub O is just V sub O over I sub O, no? Okay, so if, again, no? If input is left open, okay, then V sub I will be equal to zero. That is because I sub I is equal to zero. And therefore, okay, V sub O is just going to be equal to I sub O times R sub O. Okay. Where R sub O is V sub O over I sub O. This is at zero input or no input. Where V sub O is a test voltage. Again, kailangan natin ng test voltage. Kung wala tayong test voltage, walang magpapaandar ng mga current sa circuit natin. Okay, the last parameter is your input resistance. Okay, so let's assume we're using the Norton model. Okay, what do I do now? I apply a test voltage of V sub I, and I short the output. So what is R sub I? Actually, sa unang tingin, hindi kailangan to, no? In fact, for this particular model, hindi kailangan to. This can be an open, this can be a short. Sa totoo lang, no? Because if you take a look at this is not affected by this. Yun yung nature nga ng unilateral model. I can put anything here, and my VI will just be equal to II RI under all those conditions. So VI is equal to I sub I times R sub I. In other words, R sub I is just VI over I sub I. However, we still impose that this is at no load. Now, why do we impose that? No? So in this particular case, you see it doesn't matter. But there may be transistor topologies where it will matter. Later on, makikita niya yan, ano? There may be transistor topologies where it will matter. So why do we want this to be no load? Let's go back to the original hybrid model. Wala, yun na yun, ano? The original hybrid model. Saan ko ba here, no? Let's go back to the original hybrid model. Right? Yung R sub I, ang katumbas niyan ito, no? Yung H11. To get R sub I have to zero this out. No? And to zero this out, I have to short this. Okay? That's why when we get the input resistance, as a matter of practice, we always make the output equal to zero. We always make the output equal to zero. So, like I said, even if it looks like it doesn't matter, saan na ba tayo, no? Even if it looks like it doesn't matter, as a matter of practice, whenever we get the input resistance, we short the output. Short the output if it is the Norton model, open the output if it is the Thevenin model. Okay. Any question with regard to that? So yun lang, no? That this is the only thing that you have to remember, no? Yung no load condition. Okay, relationship between AV and GM. What is the relationship between AV and GM? if I draw my model, sorry. I want to use the Norton model now. So this is VO, this is RO, this is GM, V sub I, no? This is V sub I. Okay. In this particular case, no, this is when output is open circuit, okay, V sub O is equal to GM V sub I times R sub O. Negative. Bakit? Kasi kung ito open, okay, if this is open, then all of this current will just flow through this resistor. What will be the polarity of the voltage across the resistor? The current will be flowing upward. And therefore, the bottom will be positive with respect to the top. Kasi paakyat yung current. And therefore, V sub O is just negative of this current multiplied by R sub O. Okay? You see that? I hope you see that. If I take a look at the Thevenin model, so yung Thevenin model, ganito. Okay, this is AV times V sub I. No? This is V sub I, this is V sub O. Okay. If I leave the output open, this particular case, V sub O is AV V sub I. Right? AV V sub I. Okay. So I have minus GM V sub I RO is equal to AV V sub I. Right? So AV is equal to minus GM RO. That's a relationship between your voltage gain and your transconductance. This is assuming that your output is open circuit. Assuming that your output is open circuited. Okay. What happens when we cascade two-port networks? So let me give you an example. And for this particular case, let's use the Thevenin model. So let's say I have this is my first two-port network. So this is V sub I. This is, let me call this R1I, R1I, R0, R1O, R1O, and then this is AV1 V sub I. AV1 V sub I. Then I have another network here. Okay. So this is now R2I. This is AV2. Let's call this V of 2, where this is V of 2. This is R2O. Okay. And finally, this is V of O. So ano mangyayari kung ikabit ko itong dalawang to? Okay. What will happen if I connect the two? Okay, what happens is the output of my first two-port network is connected to the input of my second. But the voltage here is not going to be preserved. The reason why the voltage here will not be preserved is I connected a load across it. So kung meron akong load across it, no? Kung dati-dati open circuit yan, wala akong voltage drop dito, no? Pero meron load, so magkakaroon ako ng voltage drop here. Now, how do I compute for V2? Any suggestions? Can you see how you compute for V2? Correct, no? Voltage divider. Right? V2 is just AV1, V sub I, multiplied by R2I over R2I plus R1O. Diba? I have this resistor, this is my source. Okay, so this voltage is the source multiplied by this resistance divided by the sum of the two resistances. Okay. What is now V sub O? Okay. Assuming this is left open, then V sub O is just AV2 multiplied by V2. No? So this is AV2 multiplied by AV1, V sub I, R2I over R2I plus R1O. Okay. What is going to be my overall AV? This is going to be equal to V sub O over V sub I. Kung ano man yung voltage dito, this is the overall AV, no? The voltage here divided by the voltage here. No? So what is this going to be? This is going to be AV1, AV2, R2I over R2I plus R1O. Okay, what is my overall RI? Yung overall RI ko will just be RI1. No? In other words, what the source here will see will just be this resistance, RI1. So RI will just be R1I rather, R1I. And my overall RO will just be R2O. If I reduce this to 0, and I can reduce this to 0 by making this 0, no? If I make this 0, magiging 0 din to. Okay? So what is my overall R sub O? That's going to be R sub O is equal to R2O. So meaning to say, I now have a new two-port network. Okay. This is going to be my RI. This is going to be my AV, V sub I. This is V sub I. And this is going to be my Rs of O. No? Where itong AV is this. Itong Rs of I, yan siya. Itong Rs of O. Doon may lalagay. No? So I'm just showing you that when you have two two-port networks, it's possible to combine them so that you have just one two-port model that represents the entire two-port network. Just a matter of working out the overall expression for AV, for RI, and for RO. Okay, what's next? So what's next? So we're going to use the unilateral hybrid bimodal to study the behavior of transistor amplifier circuits. Yun ang gagawin natin. And what is the procedure by which we will do that? First step, determine the small signal parameters of the transistor at the transistor's operating point, and we know that you have to do this using the large signal model. Kasi para natin makuha yung small signal parameters, we need to know the Q point. To know the Q point, you have to use the large signal model. For example, if it's a MOS, alam natin that GM is, ano yung GM? That's 2 IDQ over VGSQ minus VTH. No? You'll have to remember that siguro. So I need to know IDQ. And I need to know VGSQ to be able to determine GM. No? So in step 1, we'll entail you to use the large signal model. Step 2, we draw the transistor's small signal model. The next step, idadagdagan natin dun sa model na yan, yung small signal model ng lahat ng ibang components na nandun sa circuit natin. We have to add all the other components. Okay, so what I use is your resistors, your capacitors, your inductors, and your supply voltages. After doing that now, you can now determine the hybrid bimodal of the entire circuit. Okay, medyo naubusan tayo ng oras, ano? So I'll stop there, give you time to digest what we learned. And then, okay, next meeting, habol tayo ng konti. What I'll do is, I'll discuss the small signal equivalent ito of the other components. Kasi alam na natin yung small signal equivalent ng transistor, no? But we have to discuss the small signal equivalent of the other elements, and you're going to find that's very trivial. No, ang lalabas, resistors are resistors, capacitors are capacitors, inductors are inductors. Supply voltages are short circuits if it's a voltage. Supply currents are open circuit. Yun na, no? And then we'll go into the next submodule, which is the common emitter and the common source amplifier. Okay, so are there any questions? Any questions? Okay. Anyway, I'll be here for the next 3-4 minutes or so if you have any questions. Otherwise, that's all for this afternoon. Okay, thank you.